All right, everyone, in this video, we are going to introduce our reversible reactions to aldehydes and ketones and go through cyanohydrin formation. So we said that before, when we have an irreversible reaction to an aldehyde or ketone, it's because we're reacting with a strongly basic carbon of negative charge nucleophile or a hydride nucleophile. Those added irreversibly to the carbonyl carbon of an aldehyde or ketone. But we see reversibility when we attack the carbonyl carbon. Instead, when we react with CN-, which is a weakly basic carbon, with water or hydroxide, with a neutral alcohol or an alkoxide, or even reacting with amines, those, in comparison, once they add in, are more suitable leaving groups and they could add to the carbonyl carbon and then get kicked out of the structure. So the next number of videos are going to be detailing reversible reactions of aldehydes and ketones. So let's begin with cyanohydrin formation. A cyanohydrin is a carbon where we have both a CN attachment, a nitrile functional group, the cyano portion, and an OH group, aka hydrin, cyanohydrin. We derive cyanohydrins from aldehydes and ketones when we react with NaCN and HCl. Please notice that the NaCN is specifically in excess. Now, why we have that particular preparation in excess of NaCN compared to the amount of HCl is at equilibrium, we want to have some population of HCN molecules, and we also want to have CN-, a nucleophile. Now, when we have NaCN and HCl in solution, what's going to happen is NaCN will deprotonate HCl irreversibly. That will form HCN. And if we have an excess of the NaCN, that means that once all the HCl is consumed, producing one equivalent of our HCN, we still have some CN- left over. And that's the ideal. We want to have a proton source of HCN and CN-. Now, before we get into the actual mechanism, I want to show you something really quickly. And that's this. When we're looking at the acetylide carbanion, carbon of negative charge, part of a triple bond there, that's very strongly basic. That negative charge would be less stable than OH-, and OH-, interestingly, is less stable than CN-. That carbon of CN- is very weakly basic, and the negative charge is more stable on that carbon than it is on an oxygen atom, where that oxygen is specifically possessing a localized charge. We'll relate that detail to the mechanism that we're about to cover. So when we're looking at cyanohydrin formation, we're going to react with NaCN in an excess amount and have HCl present as well in a deficiency. And then specifically, we're going to have probably a water solvent. You may or may not see water included in that reaction expression, but it would be a water solvent that we'd use. Now, first detail, mechanistically, we're not going to protonate the carbonyl first with HCN. HCN is not quite acidic enough to protonate the carbonyl oxygen. Rather, mechanistically, what's going to happen first is an attack at the carbonyl carbon by CN-. Now, once we've done so, we've technically taken the negative on the carbon and transferred it to the oxygen atom. What we set up here is that CN- is technically more stable with the negative compared to the oxygen atom. So in that first step, what we did is we transferred the negative from a more stable atom to a less stable atom because of that, and because CN- itself is a weak base. We could see that add reversibly. We can attack the carbonyl carbon, breaking the pi bond, and then we could collapse the tetrahedral structure, kicking out CN as a leaving group, reforming the carbonyl and CN-. So CN- adds reversibly to the carbonyl carbon. First step is attack the carbonyl carbon and break the pi bond. And then to stabilize that tetrahedral structure, we're going to show that O- protonating using HCN as our proton source. What that step does is it takes the O- charge. We transfer the negative back to a carbon. Remember, that carbon specifically is more stable than that oxygen negative. And that forms our cyanohydrin, just a quick two-step mechanism. We first attack with CN-, which adds reversibly, and then we stabilize the cyanohydrin tetrahedral structure when we protonate in the second step, and we specifically protonate using HCN. Remember, at this time point, all the HCl is consumed. All right. So we form cyanohydrins under acidic conditions. NaCN with HCl, we need an excess of CN-, and we have that particular preparation because we want to produce some population of HCN molecules, which protonates the tetrahedral structure, and we want some CN- left over to be able to attack the carbonyl carbon right away. And for your records, just to point this out, notice that HCN is around pKa 9. So it's a pretty acidic species, which means that this carbon of negative charge is fairly stable with that negative, especially in comparison to, say, the acetylide ion, which is much less stable with that negative charge. Remember, the terminal alkyne pKa is approximately 26, so much less stable compared to CN-. Now, let's say that you already have a cyanohydrin and you want to reverse that equilibrium to reform the carbonyl, NCN-. We would reverse cyanohydrin formation under aqueous base conditions. That is to say, that cyanohydrins are unstable to base. They will react under basic conditions, but they would be stable to acid. Okay. So when we combine the cyanohydrin with NaOH and H2O, mechanistically OH- is going to deprotonate the cyanohydrin. Once we charge that negatively, we can then collapse the tetrahedral structure and kick out a CN- leaving group. Another quick two-step mechanism. We deprotonate, forming the charge structure here. Then we eliminate CN-, and CN- is a weak base leaving group. So you might see a question similar to this on a former exam. Professors gave this sort of format for a question, and they said provide conditions for each reaction, meaning for the formation of the cyanohydrin, and then the conditions for the reversal of the cyanohydrin. When we're generating the cyanohydrin, we would want to use NaCN and HCl, and specifically, we want to use an excess amount of the NaCN compared to the HCl, and then you could have an H2O solvent. Mechanistically, we would attack first, breaking the pi bond, and then after we've attacked, breaking the pi bond, we have our tetrahedral structure here. We would then protonate with HCN, and that would then form your cyanohydrin. Two-step mechanism. CN- attacks first. We break the pi bond, and then protonate in the second step with HCN. Same mechanism as we just discussed on the last page. And if we were at the cyanohydrin itself, we wanted to reverse that equilibrium. The reagents required here would be NaOH and H2O. We would use our aqueous base to reverse the cyanohydrin formation. Reverse. And then here we have our reagents for the formation of the cyanohydrin. All right. So this reaction ultimately not too bad. Aldehyde or ketone plus NaCN in excess with HCl, that generates the cyanohydrin structure. Mechanistically, we attack first with CN-, generating our charged O- tetrahedral. That step is reversible. CN- could be kicked out and we could reform the carbonyl. But ultimately, we're doing this reaction under acidic conditions such that we can protonate that oxygen, and protonation of that oxygen then stabilizes the cyanohydrin. Okay. Now, while HCN was not quite acidic enough to protonate the carbonyl oxygen to begin with, it is amply acidic to protonate that O- charge. All right, and we reverse cyanohydrin under basic conditions using NaOH and H2O. This would be a great visual here for the formation conditions versus the reversal conditions.